I'll be quick, like the search systems we are trying to build. Okay, so we have been, for the last couple of years, building search in production, up to, let's say, 2-3 terabytes worth of index sizes. And these learnings come from trying to actually make that stuff work. And we all kind of start with the very simple idea that we'll have some kind of query and some kind of document, and the underlying database will help us find the right results based on, let's say, cosine similarity or dot product. And I think it's worth actually understanding a little bit of how this works under the hood. So let's say these are the documents. And for example, in Quadrant, we have this data structure that allows us to only look at some of the dots or some fraction of the data size to figure out what is the right document for the query, right? So we just kind of bounce around something. We look at small fraction of the data. We find the right stuff. This is efficient. This is affordable. This is great. Okay. And that's where we all start, and that's why the initial demo kind of works. But then, you realize that there is other stuff besides just the, let's say, text of your query and the text in your document. And for example, you discover that, okay, I should probably care about freshness of the results. And you basically have different ways to start caring about the freshness. But let's say you design a custom scoring function that now combines something from the metadata and the cosine similarity itself. Again, in different systems, you implement this differently. I think it's called custom function in OpenSearch. But at the end of the day, this is what drives the quality of your results. So you add this formula, basically, and now the story gets a bit messy, because basically the first part will still happen with the approximate nearest neighbor search data structure, so that will be efficient. But now it needs to find some relevant documents for the query and only look at those to compute the total score. Right? This is what we call, let's say, approximate nearest neighbor search with re-ranking. This is how the metadata boosting functionality of Quadrant works, right? And then let's say this space is ordered by timestamps, so the stuff on the left, the candidates over here, will be scoring the highest, and it will sort of fall off as we go to the right through the picture. Am I making sense so far? Yeah? Okay. Okay. So what's the issue here? Those two dudes, for example, right? So somehow those are quite recent if the time is from left to right, but they were not in the initial set of candidates discovered through just the cosine similarity between the query and the document, and so no amount of re-ranking will find us those two candidates. And this is called the recall problem, right? Now, of course, you don't end there, because your product manager has an idea and your business stakeholder has an idea. You discover that certain features are useful to actually get people to click on the results, right? They maximize your click-through rate. So you keep adding stuff to this formula, right? Let's say you have some kind of popularity score and you want to factor it into the ranking. And maybe then you get a bit more clever, because you realize that, well, actually not every user likes the same stuff. So let's cluster our users and have some buckets. And then based on where the user is, we'll have different popularity scores. Maybe this is location, maybe it's some behavioral clusters, what have you. So it's getting more and more complicated. Eventually, hopefully you find out that, well, we can describe the user as a vector as well and do some kind of distance between the user preference vector and the document, because that means that it's computed individually for each user and the document. But still, it's going to be a component in that distance function. The next thing you realize, and that we realize as we build these systems, is that, well, how do we know the weights with which we should combine these things in our custom scoring function? Those probably should also be somehow computed based on the query, based on the document. It should somehow be inferred in order to maximize, let's say, the click-through rate or the quality of the results. So we are kind of complicating this further, and we have complicated it further. And then it keeps going, right? You can kind of imagine how, basically we are scrolling through months and months of building of these production search systems, and we are accumulating complexity in our scoring function. And the recall issue that we had when we had just 2 components of that function only gets worse and worse, right? Because we have that initial retrieval, and now we are hoping that all of the results that maximize that function are somehow in that initial set of candidates. And we build those kind of systems, and then this is how that looks over time, right? It's not so good, right? The latency keeps going up, the cost keeps going up because you are retrieving more and more candidates to re-rank more and more stuff, and still you are not retrieving enough candidates to preserve the recall or hit the recall that you would want. Why? In some way, I think you should think about your retrieval, your candidate generation system on these 3 axes. So you can have a system that has very low cost, very low latency, and good recall, right? And initially, perhaps when you started, your approximate nearest neighbor search with re-ranking on top. Re-ranking could be like a cross-encoder for the text re-ranking, but also the metadata boosting kind of re-ranking that the database offers. Maybe you had like decent recall, decent cost, decent latency. But then as you start to make that function more complicated, you bring in more context, you bring in more signals, because you want to improve the results. This thing basically shrinks, right? So your system is now more expensive, slower, and the recall decreases. Right? So that's your project. This is not going to get us promoted, guys. Like this is a problem, right? It's going away from us. Okay. Well, so what do we do about this? Actually, there is sort of like a different kind of idea. What about we just scan through all the data for all the queries instead of trying to figure out how to, hop around with some kind of index data structure? Let's just be really good at scanning through all the data. The problem is, of course, that scanning through all the data is either slow or expensive, right? So you either get this kind of shape, so decent recall because you are scanning through everything, you are evaluating your function, and it's low latency because we pay a ton of money for compute to scan through all the data in the index, or the other thing, right? Like we compromise latency to get cost. So these are the trade-offs that you see on pricing calculators of the different database offerings out there, right? This is how you should understand those trade-offs. So it's just kind of not good, right? And in practice, it could look like this. So this is a cost chart for one of our projects, only one, like one of the deployments. And this is the storage component for that project. So it just, when I say expensive, I kind of mean it. And now, okay, well, how do we fix this, right? Should be the good part. Well, remember this? Like, this is nice, right? This is fast, this is affordable. So what about we just keep doing that somehow, right? So your whole problem becomes, okay, if I don't make my distance function a mess, then my system works, right? How? How do we do it? Well, it's really simple. You just take all that stuff and you somehow encode it together with the query. You take all the context, all the user intent, all the metadata, all the whatever it is, and somehow you stuff it into the query encoding. And then you do the same thing to the document, right? You figure out how to model all of this in the embedding of the document. And then you are back to this. Because now your query contains all the information required to compute the distance function, and your document has the counterpart to that. And if both of them are embeddings, then the cosine similarity that the database can do very quickly and efficiently solves your problem. Right? Is this like trivial or what? Like it's super straightforward, right? And people still, on LinkedIn I encounter people saying, why would you put a timestamp into an embedding? So hopefully this clarifies it, because I don't want to have an extra scoring function that kicks me into either a full scan or a very low recall and high cost situation. And if you do that, your system not only comes back here where we started, but actually can cover more of the ground because you need fewer candidates, you need less re-ranking, and your recall improves because now you are evaluating the whole distance function globally on all the data. Right? Because you are not doing it in re-ranking, you are doing it in the underlying retrieval. We have a framework that does this, that constructs these models. And we are about to publish some benchmarks. So this is not yet public. You can take a picture of it, but maybe don't share it. and we have compared what we call metadata-aware embedding model that can take in a natural language query and output this compound embedding that is metadata-aware with end-to-end search systems, right? So we benchmark against AI search in Google Cloud, Azure, and so on. And we had to construct our own benchmarking data set, and we will open source that, and it's a topic on its own because it has to have metadata and the text, and all the existing data sets don't have that. And with 16 seconds left, this is the end of my talk. We have the framework is open source. If any of you builds something with it and shares it with us and sends like 5 bullet points that help us then together publish an article about it, we'll give you 500 USD. And that's the QR code behind which the 500 bucks resides. That's our GitHub. Pip install Superlinked, and good luck. Thank you.